All right, so homework 8, which isn't available yet because I haven't yet written the question related to secondary settling. I'll put that online today, which means that you'll have 2 weeks to finish that before it's due on the 30th of November. So chapter 25, which is what we're covering today after skipping over a couple of chapters that unfortunately we don't have time for. You know, we went from trickling filters now to secondary settling. Chapter 25 includes disinfection, secondary settling, and post-aeration. And so we've already talked about aeration, we've already talked about disinfection. The thing that to me seemed the most unique and the most needing of some time was secondary settling. And especially because the example that's provided in the book, it's complicated and there's unfortunately an error in the way that they do it in the book. It's a minor error, but I wanted to iron it all out. So we're going to go through a pretty detailed example in class today. And if you've got your computer, you could follow along by bringing up Microsoft Excel. And if you don't, that's okay, because I've printed off something that I'm going to give you at a certain point when we get there. But if you want to follow along with Excel, I'll give you the advance warning now so that you can begin booting your computer. Okay, so let's just take a moment to reflect on what secondary settling is and where in the process it occurs. Secondary settling is going to be different from the grit chamber settling, which was just going to be type 1 settling, which assumes the particles aren't interacting. It's going to be different from type 2 settling, which assumes that the particles are actually getting larger as they settle, which may be the case in some limited cases, but by far the most common thing is going to be this type 3 settling, zone settling, where the sludge blanket is interfering with itself as it settles downward. And so there will be some initial particle settling velocity when a particle enters the top of the clarifier, but it's slowing down as you get further and further down into the clarifier. The velocity of settling decreases, and so there's kind of a backlog down at the bottom, and then the sludge compresses itself. And so the calculations and the design that we do related to secondary settling are based on lab analysis of batch samples. That is, that they would grab a sample of the mixed liquor from an aeration basin, which includes the wastewater and any sludge that's been recirculated into the aeration basin. So they grab a sample of that, and then they kind of monitor the performance of settling of that wastewater at different concentrations of mixed liquor. And so if you have a really high rate of recycle and a high concentration of mixed liquor suspended solids in the aeration basin, then in the secondary clarifier there's going to be the same high concentration of particles and the slower initial settling velocity. And then if you have a slow initial settling velocity, then the subsequent settling velocities as the particles begin to interfere and impact each other will be even slower. Okay. So a couple of basic terms I wanted to introduce at first, and then there's going to be a couple of additional equations that we use in the course of the example that we're working. The two things that we're going to be consistently comparing to each other during secondary settling is the rate of overflow solid flux and the underflow solid flux. Now, if you look at the units of this, a flux just means some rate per unit area. And so if the parameters that go into the overflow solid flux rate are the flow rate volumetric, so cubic meters per day, and then a mass concentration, so kilograms per cubic meter, or sometimes the mixed liquor volatile suspended solids, we could express that in grams per liter. Remember, grams per liter and kilograms per cubic meter are the same. But so in the numerator of this, we're going to have kilograms per day when we multiply those two things together. And then the denominator, it is per square meter. So what this is saying is what's coming into the top of the clarifier? What's the rate of us loading mass from the aeration basin into the top of the clarifier? So that's the overflow solids flux rate, is just how many kilograms of suspended solids per day are being loaded onto each square meter of top view secondary clarifier. So that's looking from above the area that we're loading the solids on there. Now, the underflow velocity is taking into account the rate that the sludge is being returned to the aeration basin. And so remember, at the bottom of this clarifier, some of the sludge will be wasted and some of the sludge will be returned. Excuse me. So the underflow velocity is looking at the underflow flow rate, which is the same as the return activated sludge flow rate. So that's the volumetric rate that's coming from the bottom of the clarifier back into the aeration basin, and then dividing that by the clarifier surface area. So these two things we're going to be using in a graphical calculation process that we go through, and the purpose of the process is to know whether the clarifier is being overloaded, underloaded, or whether it's just right at this critical point of receiving as much solids as it can handle based on the settling performance. And so we don't actually even use an equation to predict the rate of settling of the solids. We use the batch data and then kind of analyze the given area of the clarifier based on the batch data. So this is maybe a little bit more complicated than most of the things we do in this class, but I think over the course of the next 40 minutes we can probably get it figured out. So we'll do that with this example, and it's adapted from the example that's in your book, but as I mentioned, the example in the book has a couple of mistakes in the units that I think make it even more complicated than it is to begin with. So let's just look at the given data. So we'd have batch data which says for an initial incoming concentration into the clarifier, what's the initial settling velocity? And so let's just think kind of rationally about this data. And by the way, if you've got Excel going, you can start transcribing this into your own spreadsheet as I talk about what it is. So if you've got a low concentration of suspended solids coming into the clarifier, then initially the particles are going to settle relatively quickly because they're not interfering with each other. Now this is just talking about the settling velocity at the top of the clarifier. It's not talking about the settling velocity at the bottom of the clarifier, but what we know is that at the bottom of the clarifier, the concentration of suspended solids is going up. So we have to think about in the clarifier, at the top of the clarifier, it's a mixture of solids and water. At the bottom, the whole purpose of the clarifier is to increase the concentration of solids. And so, we're extracting water from the top of the clarifier through this weir, an overflow weir. So, a mixture of water comes in, clear water comes off the top, sludge comes off the bottom, and sludge is more solids than it was when it came in. So although this data is specifically talking about the initial settling velocity, part of its utility is it tells us what is the settling velocity down in the body of the clarifier when the concentration is increasing. So maybe if in this example we say that we're sending the water from the aeration basin to the clarifier at the concentration of 3,125 milligrams per liter. So from that we can ascertain what's the initial settling velocity, but then as that mixture of solids and liquids compresses, and at the bottom of the clarifier there's more and more solids, it's going to be slowing down in its settling velocity, and we can use this initial settling velocity as a surrogate for the actual settling velocity as the concentration increases. So just to look at this side view picture, just in your mind try to envision that the concentration of solids as you're going down, the concentration of solids is increasing. At the top of the clarifier, the solids concentration is just the concentration of the water that's coming in. So it would be the same as the solids concentration in the aeration basin. But at the bottom, it's thickened. So there's more solids per unit volume of liquid. Okay, so what we're going to do is we're going to consider this 35-meter diameter secondary clarifier. We know the flow rate that's coming into the clarifier, and that's the liquid that's a mixture of wastewater, the return activated sludge that's been mixed into the aeration basin. And so this water that's coming into the clarifier has a suspended solids concentration of 3,125 milligrams per liter. But then down at the bottom of the clarifier, we're sucking out a concentrated sludge and returning it to the aeration basin, and it's been concentrated up to a concentration of 10,000 milligrams per liter. So the liquid in the top came in at 3,000 approximately milligrams per liter. At the bottom, it's 10,000 milligrams per liter. And so what we want to know is, this 35-meter diameter clarifier, does it need to be that big? Or for the settling data that we've got, could we have maybe gotten away with a smaller diameter clarifier? In other words, are we loading this clarifier exactly to its capacity? Are we overloading it potentially? Or is the clarifier being underloaded based on the settling performance, its size, and the concentrations involved? Okay, so that's the setup. Any questions about, number one, the motivation for this analysis, or any questions about the setup itself of the example? So who can just rephrase, what's the motivation for why we're doing this analysis? Like, in the real world, why would a designer want to do the calculations that we're about to do?
You wouldn't want it to overflow, and you wouldn't want to underuse it.
Okay, that's right. So what would overflow look like?
I would assume it would start clogging up. The sludge would start to clog up, as well as pushing it over. You get solids coming out of the tank.
Exactly right. You get solids in the effluent if you're putting in more solids than the batch settling data says you can handle, then you'll start to see solids in the effluent. So that's exactly right. And the risk of underloading it is just an economic risk. It's just simply that you've got a clarifier that's bigger and therefore more costly than it needed to be based on the demands of the system. Okay, so here's what we're going to do. I'll write the steps on the whiteboard so that you can take notes on this procedure, because you're going to need to apply the same procedure in the homework problem that I'm going to give you related to this. So our first step is we're going to calculate the initial underflow loading rate by the batch data. So it is the initial concentration times the initial velocity from the batch data. So I'm just going to copy all of this data, and if you're following along with Excel, you would have typed it in, I think, to Excel already, but the benefit of me having it already in PowerPoint is that then I can just paste it, which is what I'm going to do here. Okay, so I've got, for different concentrations, what's the initial settling velocity? And so what we're going to calculate now, this is the underflow solids flux. So this underflow solids flux. So remember, there's two different fluxes. There's the flux of how much we're loading into the top of the clarifier, and there's the flux of how much we're removing. And with the lab data, we can get at the underflow solids flux performance by multiplying C sub I times the velocity, initial settling velocity. So let me write this underflow solids flux S sub F subscript U, and it's going to have units of kilograms per cubic meter per hour. since right now the time-based data for the settling is in time units of hours. Okay, so underflow solids flux, let me make this a little bit bigger. Okay, so it's just going to be simply the concentration multiplied by the initial settling velocity. Okay, now I've got it in, right now it's in grams per cubic meter per hour, because this was grams per cubic meter, this is meter per hour. Oh, and that's the other thing, is it's square meter, because the units cancel out there. Okay. So just to draw attention to the units here, let me go ahead and format that as superscript so that there's no confusion. S sub F. Okay. Now, I would like it as kilograms, and so I'm going to divide that by 1,000. So I simply multiplied these two together. It's going to give me grams per square meter per hour. But if I divide by 1,000, now I can say that's kilograms. Okay, and by the way, if there are any questions or if I make a mistake along the way, which is quite possible, then please let me know. I count on you to keep me honest in these ones. All right. So we've got this, this data that we're going to graph. And what we're going to graph is the concentration of mixed liquor suspended solids versus this flux rate. And so let's make a curve. We're going to just do an XY scatter plot. And so to do that, I guess maybe if I'm writing the steps on the whiteboard here, I'd say that step 2 is plot S sub F U on the y-axis and mixed liquor suspended solids concentration on the x-axis. So that's going to be where we plot this data. Okay, so I'm going to do insert and then this XY scatter plot. And I think for our purposes, it's good to have it be the curved lines, the smooth lines, rather than the jagged just connecting the dots. And I also think it's good for us to be able to see the data points themselves. So I'm going to do this scatter with smooth lines and markers type. So you insert that, and now we have to select the data up at the top. And what we want to select for this, we have to add a series. And on the X values, it's going to be the concentration of mixed liquor suspended solids. Okay, and then for the Y values, we're going to graph the underflow solids flux. And we should have a pretty nice looking curve here that is saying for a certain concentration, what's the rate that you can be settling these solids at the bottom of the clarifier. And it's rate per unit area. So the interesting thing here is you can see where the flux is the highest. Maybe I ought to add some axis titles here. So to do that, click on the chart plus axis titles. And so let's just, so that there's no confusion, this is the solids concentration, and that is units of grams per cubic meter.
Square meter, right?
Pardon me?
Square meter, right? Or am I wrong?
No, this is a concentration for now, so it's not a flux, but I'm glad that you're double checking. But on this axis, it is going to be per square meter. So this is the solid flux, which has units of kilograms per meter squared hour. And let me put that up into the superscript. Although I'm sure you could see it even if it wasn't. All right. So are there any questions so far about what we're graphing? Okay, so the point I wanted to make is that what we can see is that it seems like the highest flux is at 2,000 grams per cubic meter. But that's not necessarily the concentration that we want to operate the sludge at. Like, we may want a higher concentration of sludge to be going into the aeration basin. So it's not like we can just say, well, let's make sure that the concentration of solids at the bottom of the clarifier is 2,000, just therefore to maximize the solid flux, because there's other considerations involved. You know, the aeration basin, we're trying to break down BOD as quickly as possible. And it's likely that we're going to need more suspended solids in the aeration basin to do that than whatever corresponds to the maximum solid flux. And so we're balancing a couple of parameters. Or we're balancing, on the one hand, wanting to reduce the BOD that's being consumed. We want to use as little aeration volume as possible. You know, we want to have the aeration basin size as small as possible. And so this size of the clarifier is just one piece of the puzzle. And so I just wanted to point out that this maxima point here, that's not like the ideal operating point necessarily. That just happens to be the concentration that would maximize solid flux. Okay. But with that said, what I'm going to do, just to make it easier for us to see things, and maybe this is something you've done before, let's add minor tick lines. And also, instead of just being 2,000, 4,000, 6,000, I want it to be every 1,000 that it's indicating that. So I'll change that. So now it's every 1,000. And then I'm going to right-click. And we're going to do add minor grid lines. Okay, so now there's a lot more density of lines here, which, because we're going to be ultimately extrapolating a line in a point of tangency with the curve, it's useful for us to have all these extra tick lines here. And I'll do the same thing on the vertical axis. If you just right-click on it and then add minor grid lines, now we've got a little bit of a graph paper that will be beneficial when we're drawing a certain curve. Okay, so let me pause for a second and see if anybody has any questions about the concept or about our problem-solving approach so far. Okay, so we did part 2. Part 3 is calculate the clarifier area. Calculate the area of the clarifier. Okay, and you know, this is simple enough. Let me, by the way, bring up my example so that I can get some of these steps integrated into the lecture video. All right, so what we've done so far is step 1, calculate the S sub F. Step 2, plot the underflow rate versus the concentration. So then the area of the clarifier here for a 35 meter diameter is 962.11 square meters. Okay, so let me just write that on the whiteboard here. So the area is 962.11 square meters. And we use that because we're going to calculate the overflow solid flux. So calculate the clarifier overflow solid flux using the formula S sub F is Q times X divided by A. Now what we calculated before this, based on the batch data, this is the underflow performance because it's settling velocities versus concentration. This overflow solid flux is more about what's coming into the top of the clarifier. So it's going to be based on the flow rate, the concentration of mixed liquor suspended solids, and the area. Now, what we need at first to do is just calculate this on on the basis of the flow rate that we have in this example is 9,200 cubic meters per day. So 9,200 cubic meters per day. And for now, let's just leave x as a variable. X is the concentration of the suspended solids. And divide that by the area of 962.11 meters squared. Okay, so that is 9.56 meters per day multiplied by x, which we haven't yet substituted into. But we'll calculate it now in step 5 for our actual operating point. And the reason why we leave it for now as a variable is we may want to change our operating point. And so just having an intermediate step like this allows us to find out what would be the new overflow solid flux if we have a different suspended solids in the aeration basin. Okay, so now step 5 is for the x value that we actually know we've got, which is 3125 milligrams per liter. And to be consistent with the units that we've calculated so far, since this was in kilograms, let's say that we're going to use x as 3.125 kilograms per cubic meter. So what I've done is simultaneously changed it from volume units of liters to volume units of cubic meters. So I multiplied by 1,000 to do that. And then you multiply by, and then from milligrams to kilograms is a 10 to the 6th conversion. So the concentration of the solids in our aeration basin is 3.125 kilograms per cubic meter. And so then therefore, the solid flux is 9.56 meters per day multiplied by 3.125 kilograms per cubic meter. And that's 1.245 kilograms per meter squared per hour. That's what we call our operating flux. So what we're actually operating at with the flow rate that's coming into the clarifier and the concentration of the solid particles and the area of the clarifier, we're piling into this clarifier 1.25 kilograms per hour onto every square meter of the clarifier. So that's just how much mass is coming to each unit area of the clarifier. So what we have to do now is a graphical technique where we're going to plot the line between 0, 0 on this axis and 0, 1, and I'm sorry, not from 0, 0 over to 3,125 and then the 245 kilograms per square meter per hour. So let me give you this handout now so that we can do the sketching part of it. Okay, So what we're going to do is, it already has it plotted on the handout that I've given you, but we want to have a line that goes from 0, 0. So remember, the x-axis is solid concentration, the y-axis is flux. So the point at the origin is that there's no flux if there's no solids concentration. But then what we know is that when the concentration is 3,125, then the flux is 1.245. That's what we just calculated. Let me bring it up on the screen here. Okay, we just calculated the operating flux using this formula for the concentration of 3,125 milligrams per liter. We found that we'd be operating the clarifier at 1.245 kilograms per meter squared per hour. So I want to have like a straight line on the curve that represents this, and you already see it on the paper there, but just so that we see what it looks like on here, let me now add another series, and it's going to have the x values are concentration, the y values are the flux. Okay, now I want this line to actually extend further beyond it, so if you've got a straight edge, continue the line beyond and through the existing gravity flux curve. So I didn't bring a straight edge, but maybe you've got your credit card or your wallet or something. Just extend that line to the point of intersection. So it should look something like, I can draw like this on here. It's going to go through those 2 points and beyond. All right, so I've got a point of intersection. Now, the next part of this is I know that the, by the way, I'm going to erase what's on the whiteboard. Does anybody need me to take a moment before I do that? These steps. I've just done step 6. Step 6 is to draw that line and intersect the gravity flux curve. So let me write what step 6 is. Step 6 was draw line from 0, 0 to 3125 grams per cubic meter, comma 1.245 kilograms per meter squared hour. Okay. I don't think I mentioned it yet, but there was a time units conversion here as well. If we have a concentration of 3.125 kilograms per cubic meter and 9.56 meters per day, so that gives me the units in terms of days, but for me to be able to graph this on the curve that we came up with, which had units of hours, I just divided by 24. So it's here. I think I jumped straight to the point, which was that it was in units of hours. But you do have to make that time conversion. Okay, so you can see step 6 is that we're going to draw the line, and that's the overflow rate operating line. So you can sketch that, label it on the handout I've just given you. Label that as the overflow rate operating line. Okay. So step 7 is we're going to draw another line onto this figure. So step 7 is plot curve from the concentration of the return activated sludge, which is in our case 10,000 grams per cubic meter, tangent to the gravity flux curve. Okay, so from 10,000 over here, we're going to draw a line that intersects, this is the gravity flux curve. So if I'm doing labels here, maybe I could insert these labels just to help keep it clear. How do I, okay, here we go. This was the gravity flux curve. This one is the overflow rate operating curve. Okay, so this third curve that I'm going to be drawing is from 10,000 and the y equals 0. So let me just draw a line. So from this point in the corner, and we want it to go up until it intersects the y-axis, but we want it to be where it's just barely touching the gravity flux curve. So this is too low because it's not touching yet. This is too high because we've crossed it. So you want to have the point of tangency. So where does it just barely come into contact with that curve? And to my eye, it's right about there. Okay, and what it's pointing us at is that the limiting flux here is 3 kilograms per meter squared per hour. So we've plotted the curve. Now step 8 is identify the limiting flux. Okay. This clarifier could handle, in our case, 3 kilograms per square meter per hour. That's the limiting flux. How much are we actually putting on there? Well, from our earlier calculations, we found that we're only adding 1.24 kilograms of mass per square meter per hour. So we are underloading the clarifier. And let me show you an illustration of how we know that to be the case. But this clarifier is underloaded. The point where these two curves intersect has some significance. See how we extended this curve? The set point where these two curves intersect helps us to diagnose whether the clarifier is being overloaded, underloaded, or it's right on the verge of being critically loaded and 100% efficiency. But before I move on to showing you kind of those diagnosis figures, are there any questions about the curves that we've drawn? I guess maybe I'll label these points since I've done it already with the rest. So this point that it's pointing at is limiting flux. We've pointed ourselves towards the limiting flux, which here it appears to be 3 kilograms per meter squared per hour.
So how did you deduce it was under?
Okay, so we will get into that. For one thing, we can see that so my conclusion, the clarifier is underloaded. And so indicators, the first indicator, the limiting flux is greater than the operating flux. So our operating flux that we had calculated we said was 1.245 kilograms per meter squared per day. So that was our operating flux, and the limiting flux that we've established by this graphical method is it's 3 kilograms per meter squared per hour. Oh, hold on a second. I just wrote the wrong units here. It wasn't per day. That's per hour. Per hour. Okay, so the units are the same. So indicator 1 that the clarifier is underloaded is simply that the limiting flux is higher than the operating flux. Now, let me show you some figures, but before I go into these diagnosis figures, are there any questions specific to like the calculations or the drawing that we've done? Okay, so these are some figures that the book presents to help you diagnose whether the clarifier is overloaded or underloaded. So let's see if we can do some pattern recognition here. You see the set point is the point of intersection between the two curves. But in the case of an underloaded clarifier, what you have is a set point that's below the gravity flux curve, and the underflow rate is not in contact with the gravity flux curve on this declining limb. You know, it crosses the gravity flux curve on its way over to the y-axis, but the point of tangency is kind of this maximum operating point. Is when you've got the limiting flux tangency curve. If it's bumping up against the gravity flux curve, then that's the maximum that you can handle. And so since this is how much we're actually doing right now, is we are going from 10,000 through our set point. So we're loading it less than the maximum amount that could be tolerated. So this shows a critically loaded curve, because in this case it's critically loaded because our actual underflow rate, the rate that we are loading, is intersecting the gravity flux curve. So our actual loading amount in our case, you know, this is, maybe I'll make this one dash just to draw the distinction between what we could achieve and what we are loading it at. Okay, so the dashed one is kind of a hypothetical of how much you could load this clarifier at. This is how much we are loading at. So the set point is below the curve. This tangency, this is not coming in contact with the gravity flux curve, and so, you know, that's kind of the visual indicator that we are underloaded. This would be case A. We are operating the clarifier at case A. But if you find that you've gone through this process and your set point intersecting with the concentration of the mixed liquor suspended solids in the return, so like in our case 10,000, so if you draw that curve and you are touching up against the gravity flux curve, then that means you're critically loaded. You can't go any more than that. So here, this is showing overloaded because they've done that very thing. They've got the underflow rate is above the gravity flux curve. So you'd be overloading it, and you're likely to see solids coming off the top of the clarifier in a case like that. Here is just another illustration of a critically loaded clarifier. And this is showing that the set point can actually be on the gravity flux curve, that's acceptable, but you're right at the limit of performance in that case. And then all of these other ones are overloaded. If the set point is above the gravity flux curve, then you're overloaded. Here's just an illustration of the set point is on the gravity flux curve, and also that tangent is above the curve where it should just barely be touching it. So you'll get a chance to apply this same process to a situation and tell me in the homework assignment if the clarifier that I'm describing to you is overloaded, underloaded, or critically loaded. And so the process that you should go through would be this same 8-step process that I've outlined for you today, combined with, a graphical and kind of a sketch process where you can draw the lines in Excel and have an idea of the solid flux it's pointing to. All right, so that's all the time we've got for today. I'll get that assignment posted this afternoon, and then you can get started, and you'll have a week to complete it. 2 weeks. All right, have a good day.